Hello and welcome to this IET sector debate. My name is Gordon Attenborough and today I will be marshalling an interrogation and examination of one of the most talked about fields of engineering and technology today, additive manufacturing, or 3D printing if you prefer. A technology that has been around in some form since the 1980s, its surge in development and interest over the last couple of years is undeniable, capturing the imagination of industry, academia, the public, and of course the press. It is now regularly touted as the next industrial revolution. To examine that statement and to discuss the subject as a whole, I'm being joined today by four prestigious panelists who cover the full spectrum of additive manufacturing. On my far right, we have Dr. Christopher Tuck, Director of the EPSRC Centre for Doctoral Training in Additive Manufacturing at the University of Nottingham. Closest to me on my right, we have James Buchanan, a prototype technology specialist with Jaguar Land Rover for the last 2 years, and currently working on the next generation of both Jaguar and Land Rover marques. On my immediate left is Dr. Phil Reeves, the Managing Director of Economist, a consultancy to industry for the implementation and application of additive manufacturing technologies. And on my far left, we have Chris Ellsworthy, the Managing Director of Cell, a company that we recently visited in Bristol who has just released a new type of 3D printer for the home called Robox. So, the first statement that we had was about this technology being the next industrial revolution. There is obviously a lot of hype and hyperbole regarding this technology in the press. Chris, do you find that irritating? Irritating?
No, it's confusing. It can be confusing to both the public that are listening to the articles and reading the words. But really, it's about getting the technology in the limelight, which is good.
Indeed. I mean, getting the technology in the limelight, any form of energy and technology, is good to get it in the public eye. But is it the right sort of publicity, Phil?
I'm not sure it's the right publicity in that what's happening is there is a perception that additive technologies, 3D printing, is a complete solution to manufacturing at the disrespect of every other technology, and that clearly isn't the case.
But surely, Chris, for somebody who's operating in the domestic market, you want as much publicity as possible.
We do, but the problem is it's slightly missold to the general public because it's sold through the public as something that's going to replace every other type of manufacturing technique that's ever been brought, and it's not that. In my mind, it's a slightly new manufacturing technique which we have to think and work on how to design products for.
I think I can agree with Phil and Chris on this, but the media hype in some ways is good. It brings the technology to the limelight, it brings it to the fore of people's minds, but it has to be the right measure of media hype. It has to be correct. It isn't a catch-all manufacturing technology that's going to solve all of our problems. It might help with a lot of them, but it won't solve everything.
But again, if you take it, actually I'm going to turn to James on this one. Obviously you have a very industrial perspective to it. But I think as an engineer as well, one of the biggest questions is about skills, engagement of young people, drawing people into engineering. And I think, is this a technology that could act as a type of Raspberry Pi? Do you think there's an inspirational basis to it?
Yes, completely. I think this technology fundamentally is exciting. It's something that you can have a 5 to 10-year-old 6 inches away and actually doing this thing, compared to a process such as casting where you've got horrendous health and safety hazards. So I think this is a brilliant technology to enable a younger generation to get into engineering.
Do you think it's a technology that means that anybody can innovate?
The question is basically premised on the fact that anybody can innovate and not everybody can. And so not everybody is interested in engineering, not everybody is interested in making products, but for those that are, and those that have the skill sets and the natural abilities, then it can enable the innovation. But it enables it. It doesn't. It's not a catch-all for seeding innovation. It enables innovation to happen.
I slightly disagree there because I feel that given a tool, someone will step up to use it. Whereas tools before, let's talk about the younger education thing again. If you give a young child a circular saw to make himself something, he's more likely to chop his fingers off. And if you give them a 3D printer, it's a safe technology. The realms of what they can produce from that 3D printer are pretty boundless. So if giving someone that tool, you've got to be able to incentivize. You're giving them an inertia at the beginning to be able to innovate.
And Chris, we've obviously talked a lot about innovation earlier on from a domestic setting. This has got to have huge implications, surely, in an industrial setting, that quick turnaround.
Yes, it does. And the quick turnaround is the original reason why these machines were developed. It was literally to streamline prototyping within industrial environments. The key now is that the cost structure of those prototypes was so high that you only wanted to do it for prototyping, and the materials are a very big issue. But as the costs come down per component, and every component can be individual, well, then you can start to make low to medium volume versions of whatever it is more viable to take forward as a complete product.
James, turning to you, you use it for prototyping. Perhaps you could put some flesh on those bones. How exactly is it used in an industrial setting for your company?
So we, like I said earlier, we never actually sign off a prototype part off the basis of a 3D printed part. It would always have to go to a representative material and a representative process. And the reason for this is that there's roughly 600 or so materials that you can 3D print in, and there's circa 20,000 industrial grade plastics. So the chances of the engineer that's come to me being able to match up his material properties to his industrial spec is minute. It just doesn't happen.
That seems quite a tempered view, but let's look at the positive sides of it. It has revolutionised prototyping, hasn't it?
Completely. I mean, if you look at the average time to get an injection molded tool, you're talking 6 to 8 weeks to getting your first part off. Whereas now we can, with some processes, I think particularly Stratasys object machine, you could have a part within 12 hours. So the time saving is massive, and I can within a week I could have had 3 or 4 different iterations of that same prototype part and got to my end component within 5 days.
I wanted to counter 2 points that you guys have made. The first being that what we've been talking about primarily so far is prototyping parts and things which are meant for other manufacturing techniques. And I strongly believe that 3D printing can go beyond those scopes and become a manufacturing technique in its own right. And the second point you were saying is about the materials that are available. I think both you guys were, and the cost of those materials which you use. And that's very much dependent on the type of process that's being used. I mean, the more kind of expensive and more precision prototypes in techniques use very expensive resins to produce your final parts. But if you want a technique which uses the actual final material that you want your part to be in, there are now technologies available which take that raw material and make your final part from it. And why then take that final part and make it in another technique seems a bit idiotic to me. Why not have the 3D printing process make the final part?
I completely agree with your second point, and your first point actually. So the whole reason that we do research in this area is because you have to marry design, the manufacturing process, and the materials. There's a loop between all three, and if you want to do additive manufacturing, you should design for it. Mm-hmm. But in terms of materials, there's still not the palette available that people are after. There's a huge amount of research that people need to do in getting the right materials, whether they be polymer, ceramic, or metal, raw materials, to get them right to a standard and quality that industry needs, I think.
Now, the one conversation that I've been hearing more recently with regards to materials is a cost implication. So obviously certain materials are very expensive and only confined to industry. But there's a new issue that's coming up, which is a question of patents. And people are actually designing materials for additive manufacturing and then patenting them. So are we becoming a situation of photo printers Mark II, where it's not the machines that's going to be the expense, it's the proprietary inks that go in it?
I don't think that's a new thing. I think that since additive manufacturing has been around since the 80s, the companies who have produced these machines have automatically tried to close off the materials that you use in them. If you look at the likes of Stratasys, EOS 3D Systems, they all want you to use their own machines. In fact, in Stratasys, you can only use their material. So I don't think this is anything new, and I think we had a conversation earlier with regards to the commercialization. At the end of the day, people only want to produce materials and machines to make money. That's what they're in it to do, and by patenting their materials, they're effectively getting ahead of the market.
But it's counterintuitive to I can see it working perfectly in prototyping. That's fine. But I think as we make this transition towards manufacturing, it's counterintuitive to just about every other manufacturing process. You don't buy injection molded resin and pellets from your molding machine maker. You don't buy billets of titanium from your CNC machining vendor. You have choice in a free market economy. So I think at some point somebody will have to challenge this. Either they challenge it commercially or it's challenged legally, and that could be an interesting context. If it's seen that this control of the supply chain is actually stifling the growth of the industry, then we may get some European Union precedent that says, well, we bring in a block exemption. We take away the ability to control the market because you're repressing the use of the technology.
I think it's already being challenged by the fact that this open source design technology environment that we live in now, where the consumers are very used to choosing maybe a 2D printer because of the cost of the refillables, not because of the quality of the machine itself. So now that we're used to making that decision not based on the quality of the machine, we're used to making the decision on how much is it going to cost to run this machine, how much are the parts going to cost. The decision to buy the hardware will be now driven by what you're going to use in it.
But there is a clear distinction. I mean, what you're talking about, the home market, absolutely agree. But if there's a situation where people are patenting industrial materials and you cannot make a certain type of product unless you've got titanium 346 or whatever, but that's owned by a particular company, that's a huge issue, surely.
Again, there's almost another precedent in what we have today, in that the polymer processes do tend to be quite tied down. The metallics don't. The metallic processes, because there's been an industry developing metallic alloys for powder metallurgy and gas atomizing and all of those kinds of things, they're relatively open for using whatever material you want. They might prefer you to use their own material, and they might offer guarantees on their own material and warranties and things like that. But in effect, you're free to put whatever you like in there. And a lot of the machines allow you to put whatever process parameters you want in there as well to get that material to work.
Well, let's flip it on its head then. Isn't this a huge opportunity to start creating materials that are suitable for industrial additive manufacturing and locking them down?
I think it is, but you then have the realization that these machines are still productively quite slow, and therefore that manifests itself in relatively low volume consumption of material. So if you take an industrial laser sintering machine, if you can push 2,500 kilos of plastic a year through it, then you've done very well. Well, from an industrial polymers perspective, you could process that on one injection molding machine in a day. So if you're making polymers, which way do you want to go? Towards the plastic molding market or the additive market?
With completely agreeing with you in effect. If you look at the largest producer of nylon, DuPont, a sintering machine has run on nylon since 1987. DuPont have never entered the market. And there's a reason behind that. The economics don't add up.
So we've talked about materials. Do you think this is one of the key technology innovation areas that needs to happen to progress additive manufacturing as a whole? Is materials the key barrier?
I think one of the big barriers at the moment is software. If we are going to design parts for the additive manufacture process, the parts are going to become a lot more complex. Now, am I going to pay a CAD engineer days and days and days to sit in front of that CAD machine and produce that part? There needs to be a fundamental shift in the way that we design components, because all of the current CAD packages lead us straight down towards traditional manufacturing, which isn't what we want to do. Because like we said before, the economics don't add up when you try and graft traditional manufacturing onto 3D printing.
Phil, I'm sorry, I'm going to be contentious here. I see you nodding there, and yet we've spoken about the fact that you have to design for traditional methods, because ultimately it'll be traditional methods that are employing it. And yet, you know, when you're talking about, well, actually, we need to fundamentally shift the software so that we're designing completely new types of product, there's a conflict there.
Well, I'm not sure there is a conflict, because I think what we're saying is that at a much earlier point in the product design and innovation cycle, you're making a decision to say, do we go down a traditionally manufactured route using moulding and machining, and we design that way using those design tools, or we make an economic decision that says, this is a viable additive product, therefore we will design it additively, we will make it additively. The problem actually comes if that's a highly successful product, where you then start to make an economic argument to use traditional processes to make it, only then to discover that you've got to go all the way back up your design cycle to re-engineer it to make it traditionally. So I agree, we need design tools that allow us to speed up that design for additive process. But we also need tools further back in terms of modelling and simulation, business modelling tools, cost modelling tools, ways of assessing the economics of using additive before we start designing for it.
We have an opportunity now, with going back to your simulation package, we do have an opportunity to allow the simulation to drive our engineering products, rather than creating a product that we know can be manufactured and then using simulation to check that it's not going to fail. We can flip it, and we can have simulation that optimizes our part first and then produce the part. And I think we're not exploiting that as much as we can at the moment.
And why is that?
Because of the way our education, the way we've been taught for generations that you produce something that's going to be cast. So in our head, when you sit down in front of a CAD machine, that's effectively what you go for. You start with a block and you take stuff away, and that needs to change, and it needs to start from an education point.
So is that going to be a cohort issue? We're going to have to wait for this next generation to come through, or can you teach an old dog?
That brings us full cycle, doesn't it? Because we're talking now about putting these tools, these machines, in the hands of the very young, so they can get used to using them as a manufacturing process of their own to build for the future. And the software is, for me, the really big sticking point, because how many of my consumers will know how to use a 3D drawing package to get the real result they want? So we really have to think about the software and how easy it is to use. And I mean, the old Star Trek replicator is the dream, really, where you mould your cup out of plasticine or whatever, and you make it your personalised. You put it in the box, you tell it what material you want it to be made from, take the cup out, and there is produced your cup in whatever material you've chosen to make it.
But the thing is with that is you're still talking about pre-existing items or parts or products. Surely the opportunity here is to start designing things completely different to that, and you're going to need a lot of skill. It's not accessible, surely.
Well, that's what I'm saying. Remove the skill from the process. I mean, if modelling in plasticine, anyone can do that. I mean, you don't have to model in plastics and metals and stuff to make your thing in metal and plastics.
But you have to take into account the engineering requirements of whatever that component might be, because that's where you choose materials, it's where you choose processes, it's where you choose design. And so if you're going to, I agree the software is a massive issue. For me, there's three. There's the materials and the processes, the design systems, and how we implement it, the business processes. But we've only recently had design simulation software and design systems that can optimize, use genetic algorithms or whatever it might be, to enable us to take in boundary conditions and force that into a design space and then get the component out that is ideal for that environment. There's the consumer angle and there's an industrial angle. It just depends on which way you want to look at it, I think.
I don't think, I mean, there's no argument that we will see more and more design tools migrating into the home. HTML5 based, browser-based software tools are incredibly powerful things now, and we can design in them. We can design with our mouse and in our browser environment. And with intelligent back-end systems, if it asks us the right questions and we answer in the right way, then we can design something that, yes, happens to be a cup. It does happen to be waterproof. If we know it's going in a dishwasher, we know it's going in a microwave. If the system asks the right questions around the product, then we can design it in the right way, or the system can design it. But it's having that foresight to think, well, what are all of the questions you need to put into a consumer-facing product that ordinarily reside in the heads of a very skilled, educated engineer? Because ultimately, that's what we're saying.
So, bouncing off your point, do you not think instead, going from a consumer angle, instead of having instead of having home users that are CAD trained, why don't we have cloud data that I want to design a cup, I've got 50,000 unlimited amounts of cup designs that someone has designed and I know is going to work on the internet. I can just pull that data off. Because fundamentally, you're talking about a limited proportion of the population that's going to be prepared to A, learn a CAD system, and B, be prepared to spend an entire day, week, month designing what is fundamentally a drinking implement.
Yeah, I agree. I think what you will have, and don't get me wrong, I don't envisage that we all have fully functional CAD systems. I think what we will have is tools that allow us to personalise and to optimise the product. So it may be as daft as it sounds, but it may be a tool that is specifically for cups because it happens to be on a cup retailing website. It may be for toothbrushes because it happens to be on a toothbrush retailing website. It may be for toys because it's on a toy vendor's website. And that's the power of the internet, in that we can jump from one place to another. We don't have to have one centralised piece of software.
We talked about designing your own things a lot. But mostly, I like the look of your cup. I want one of those, and and that's never going to go away. I mean, that's the way that trends are always set, and stuff like that. And with 3D printing, I mean, you could have those things in your house almost immediately. I mean, another problem we haven't talked about is the time it takes. We talked about it being rapid. It's rapid prototyping, but the truth of it is, rapid's relative against other things. Yeah, and. Yeah, expectations are a big point, especially when you're talking about making one. I only want one cup, and it might take 8 hours to print that cup, but it takes 6 weeks to make the tooling to make that cup. So,
but it's got to be a like-for-like comparison. Yeah.
Yeah, but equally, if that 6 hours is only 6 hours, that's fine. But invariably, unless you've designed for process and you understand process, you will try and print it, and it may fail. And then all of a sudden you wake up in the morning to a tangled mess of spaghetti on your machine, and it's a failed build, and then you have to start again. And then you question why you didn't go to a well-known online retailer and simply buy it for delivery by 9 in the morning. Because in many cases it is quicker to use a traditional supply chain to get a product.
But you've gone full circle again, because the thing you can buy online is only of someone else's choosing. If you want your name or your friend's name on that cup, you can't go to those well-known online retailers and order it for 9 o'clock the next morning.
You can if that online retailer has a regional manufacturing system. So rather than having distribution warehouses, you have distribution manufacturing centres. I think is the compromise in between.
So at some point in the process, there's been a rapid prototyping or 3D printer involved.
But not from a desktop point of view. So again, apologies, but it would be a large industrial scale machine that is vastly more capable than what we currently see in the consumer market.
That depends on the bed size. So that you want 50,000 cups made, is it more viable to make them on a machine that can do all 50,000 at the same time? Or is it more viable to have 50,000 machines that can do individual jobs by themselves? Because if you've got lots of machines doing individual things, they stop and start at different times. You don't have to wait for a whole build to be ready to put on. You can literally start individual items individually when they're wanted.
We're starting to get into the realm of dirty secrets of 3D printing and the fact that maybe the technology doesn't quite live up to the expectations as we were talking about earlier. Let's go through some of those in a bit more detail. So one of my personal favourites is supporting structures. Let's start with that one, Chris.
Supporting structures. This is a legacy left over from using a machine that's designed to print something in laminate layers to print something that is not for its process. It's not designed for its process. Designed for its process, support material isn't a structure. You can design it without support material, and you can build a functional part without the support material. Alternatively, if your object is more organic and you need support to make that organic shape, then you have bi-material printers which use one support material and another one for the final object, which are around now and being used all the time.
So are there different processes where support structures are not required at all?
So in the sintering process, you work on a bed process. So as soon as I finish printing effectively one component, I only need a small 2-3 mil gap, and I can start printing another layer because it's all self-supported within that bed structure. But that said, there is still waste around that because that powder has still been exposed to a heat cycle. So it's still, even if it hasn't been used in the print, it still comes out as used powder and it's never treated as new powder again. So with support structures, I'd agree that with you on the FDM side, you can mitigate some of the support structure need, but there are other technologies, the object polyjet process, SLA, and to a certain extent sintering, especially metal sintering, direct metal, all requires support structure, which is all waste.
Hugely wasteful though. Hugely wasteful.
But by your argument, all of those other processes, with the exception of the metals, you could design the product around not having support structure. So what you're saying is, yes, that you can mitigate support structure, but you do that at the penalty of design freedom. And one of the big benefits that we've heard for so many years is that we have this enormous flexibility and freedom of design. So we actually do have design for manufacture rules creeping in. So there's a dirty secret in itself.
Yeah. You're assuming that you have design freedom with traditional techniques. I mean, a traditional tool opens and closes and you can have side actions in there.
So are we holding it to an impossible standard?
Yes, we are. I mean, there are design for manufacture rules for traditional manufacturing. That's what everybody's taught in university, and that's what engineers use. There are design for manufacture rules for additive as well. It's just they're slightly different. And for support structures, it depends on the process. The powder bed processes for polymers don't need them at all. For FDM and pretty much every other process you do. But again, it comes down to what kind of process do you want. There may be materials that you can put down which can support but don't have any mechanical impingement on the thing that you're making, so you don't have witness lines or anything like that on the underside. So it depends on how you want to take this forward. Are support structures a really big issue? Not really.
So let's move on to one that perhaps is, which is a question of consistency and measurement, and actually verifying that what you think you've printed, you have actually printed. Is that a bigger issue, Chris?
Yeah, for industrial additive manufacturing uptake, absolutely. And closed loop control, measurement, metrology, NDT techniques are all things that a lot of people are getting very excited about, and partly for the opportunity, but also for the challenge that is there, because you're making something, you're effectively converting material in real time. It's not, you've got a billet of material that is perfect and you've checked it all, you know, it's not got any porosity in it, and then you're going to machine your component out of it. You're making the material as you're making your component. And so you have to be very sure that what those processes are happening the way that you want them to. At the moment, we're not there in terms of consistency and quality, but we're getting there. But the other thing is you have an opportunity with additive of going back and repairing things, because you're doing it layer by layer. If you do spot an error, well, you can repair it. You can possibly go back into that layer and, you know, put some more laser energy in here, or add a bit more material there from a different type of deposition technique. So there is big opportunity in that area as well.
So, Phil, obviously you have industrial clients. Is that a big issue for them?
Yeah, I mean, repeatability and the ability to validate the products that you've made. You know, the other thing that we don't have is a significant number of standards. And that then becomes a problem within supply chains. How do you communicate requirements through a supply chain if you're in aerospace or automotive or medical devices? So yeah, the ability to validate the manufacturing process is absolutely key, and knowing that what you think it is printing is what it has actually printed. Now, at the moment, we don't, and as Chris says, a lot of time and effort spent on things like non-destructive testing and X-ray. That all adds to the cost of those component parts, and again, that goes against us when we're looking at those economic models.
I mean, James, you've said on a number of occasions that, you know, you are purely focused on prototyping. It's the only use that Jaguar Land Rover have for this type of technology. You know, is this verification, this consistency, is that one of the barriers?
Yes, I think it would be. I think it definitely is, actually. I think you have to be sure that what you're producing is the same, not only from what you've designed it, but in between parts. I mean, if you're producing 100,000 cars, you want to know that every single car is exactly the same and will last and behave in exactly the same manner. And until that point, it is going to be a large barrier. But I don't think it's the main one. I think the main one is still the cost.
Indeed, and we started off this conversation talking about the misapprehensions, the misrepresentations of this technology. And we sort of dampened down, I think, over the last few minutes, what this technology is capable of. But let's lift it up again. What are some of the core projects, some of the things that you're involved in that you think people need to know about? What is a really good representation of the excitement of additive manufacturing?
I think the project I always come back to is the one that pulls all the strands of this together, and that was something called the Roband project. Which was really a number of people around the world collaborating together, using the internet as a collaboration space for design, and helping somebody out with a prosthetic hand because they didn't have access to it in South Africa through their own healthcare system. And that spiraled, that became viral. That data was shared, that file was shared. I know the guys at Nottingham, you've modified it, used your design capability and printed an amazing version of it on industrial 3D printers for a young boy. And that's a country mile away from the version that was only a year ago in South Africa. So I think, you know, that idea that we can develop things, we can virally share them, we can market them, we can test them, we can innovate and iterate. I think that's fantastic. That's where this technology absolutely fits perfectly.
I think that's a societal and a global opportunity, which is perhaps something, Chris, you can...
Yeah, it's exactly the point I was trying to make. It's the fact that even, I mean, that was an expensive machine being used to make an expensive component, but even at the very basic level, the very basic machines can really have a huge positive effect on our society, and people can be given. I keep talking about these tools, the product to manufacture the ideas they have in their head, and I know and I understand that a lot of people can't handle or be creative and innovative in their design, but surely we're going to unlock more skills and more brilliant people by giving them these easy-to-use tools.
I think for us, additive manufacturing is a tool in the toolbox. It is exactly one thing that should be considered, but it's the things that it enables which is exciting. So for us, and for me personally, the stuff that we're doing in our centre on multi-material printing, whether it be for pharmacological, food-based, whatever, is really where it's exciting, because you can actually start to really dream about products that you wouldn't normally even think about. So, cell printing into sensors, sensors built into components, so they know when their end of life is, and they know when they need to be changed, and they can tell you. Those are the kinds of aspects which, from a technology perspective, is really the exciting thing for us at the moment.
I actually wasn't going to use an example from the automotive industry. Just this week, I read about 3D printed liver cells in a scaffold that have reacted in the same way to toxins that a real liver would. And it's one of the stories that actually made me stop the office around me and get them to read it, because the opportunities there are phenomenal.
So it's been quite a considerable conversation about the current status of additive manufacturing, but let's talk about the future. Is it like the Olympics say, stronger, faster, longer? Where are we heading?
I mean, one area that really should be benefiting is within consumer electronics, and we're seeing other really impactful things happening, like Raspberry Pis, like Arduinos, like open source hardware, open source software, Android, the ability to innovate complex product. We're in a position we've never been in before, and the ability for 3 students from Birmingham University here to spin out a company and compete against the Bosches and the Samsungs of this world. They need to package those products, and they need to do it on a low cost base, and they don't understand their market or know their market. 3D printing is perfect, and I think what we're going to see is a mashing up of technologies, then open source robotics, and we're going to see this is all going to be one ecosystem of manufacturing that's a new type of manufacturing, and maybe that's the revolution. This is a tool that fits in that revolution.
I mean, it's a common status in the UK that we're really good at the innovation, not so good at the commercialisation. Do you think that's the status for this technology as well, James?
I think you're probably correct, yes. I think it's a shame that we have such a huge research base within this country. There's around 100 different institutes that are researching additive manufacturing, and yet we don't have our own large-scale machine production in here. We have all these different institutes, and they're all using the likes of EOS and 3D Systems and Stratasys, which are German, American, and the latter being Israeli.
So as one of those centres, do you bemoan not having a UK machine?
No, because we do. There is one UK, the UK's only additive manufacturing producer, which is Renishaw, which bought the MTT group not so long ago. It's one type of technology, so it's selective laser melting for metals, but that doesn't necessarily mean that it won't spin off. They were all one technology to begin with, and they're relatively new to the market. But in terms of research, yeah, we use what technology we feel is appropriate at the time, and our big thing in the EPSRC centre that we have at Nottingham is that what we want to do is move to multifunctionality, move to multiple materials in the same component, so you're actually building a system. You're not just building a component, you're building the entire thing. So moving towards this Star Trek replicator kind of idea, but in the realms of reality where you're having to deposit different types of materials.
Flesh that out for me. What are you talking about creating? Is it printing a camera, or is it just printing something that can send data back for more advanced prototypes?
So at the moment, being able to send data through a component or having sensors added into components as you're building them. But the premise is really about having the design system design our wonderful topologies that we can have in additive manufacturing, but also incorporate the necessary sensors, structural health monitoring type aspects within it, taking that into account in the design package, and then printing all of that in a single component system. And so you're actually literally building the electronics, you're building the sensors, you're building whatever it might be into your component as you're manufacturing it. Long way to go, like tens of years to go, but you can already do some parts of that already with conductives and optical circuitry and things like that, and biological circuitry as well.
I think that is the beauty of this technology. It really does come out with stories that capture the imagination. But there are barriers. We have discussed many of them, and perhaps I could focus them down to individual issues for each of you. And James, turning straight back to you, you only use it for prototyping. One of the holy grails has got to be the use of additive manufacturing on a larger scale within the manufacturing systems. What's the barrier? What's the key innovation? What needs to happen to make that step change from your perspective?
I think an immediate step change would be if we were to see the likes of a DuPont or a SABIC come into the industry and just massively cut the price of materials. That would instantly make it a viable option for our current design of parts. I think it's probably unlikely, and I think what's more likely to put us into an additive manufacturing for mass manufacturing would be when we can see we can use the benefits of the technology to produce better cars effectively, something that in a way that we wouldn't be able to do with traditional manufacturing.
Now, Chris, earlier you talked about it being something that's in the toolbox, and perhaps the next step will be hybridization, integrating additive manufacturing as to one module of a production line. Yeah. Is that the key innovation step for you?
In some ways, yes. It is a manufacturing tool at the end of the day, and the UK needs to innovate on that manufacturing tool and whatever else they need to produce their components. But I agree with James. I think the materials are the barrier, whether it be cost or reliability or whatever, are the barrier for a lot more people taking this technology up.
Phil, it's the economic argument for you, isn't it?
I guess it is, and to me, one of the big barriers that we see as a company, we've done a lot of forecasting studies, is as the material cost comes down, I'm sure it will, whether it's through third-party attrition or whether it's through the vendors changing their business model, the materials will come down in price, the productivity will go up, that will impact on the piece part economics. My biggest fear is actually that labour cost becomes a very large part of that, because these technologies, although we perceive they're lights out, there's actually an awful lot of labour involved in the loading of the machines, certainly the unloading of the machines, the cleaning up of the models. It isn't as automated as something like an NC machine or an injection molding machine. I think we need to start thinking now about how do we automate some of these processes, because otherwise they will still only work in low-cost labour economies.
Chris, I'm going to be a little bit presumptive and I might give you your answer. Okay. You're very much about the global and the social objectives. Surely legalities and legal issues could be the fundamental barrier to innovation, how you see it.
They are, and it's a really fine edge for us to walk on, because I'm a commercial entity. I need to make money from this technology, and I use patents to protect my intellectual property in that field. On my other hand, I want to give everybody the designs for my printers. I want to enable everyone to manufacture and produce their own products. And so I'm running this very thin line between commercializing a product which I want to give to society to help build their, the social economics of it. So, but on the other hand, I believe that it's people like us who are looking into this technology in a really strong way that will help society to grow anyway. So without me commercializing it a little bit, I can't pay for it to move forward.
Now, I don't know if you agree with this, but one of the assertions has been that the big surge in development over the last couple of years is actually because patents have been expiring, and therefore people can start investing in exploring this area. Do you think that's right, Chris?
In part, yes. I think because certain patents have expired, the proliferation of that type of technology is increased, and that's only going to increase because most of the patents are coming up in a 5-year time frame, or something like that anyway. And so with a bit of luck, you'll see a lot more innovation and a lot more different types of processes happening because of that. But I don't think it's the only reason. I think part of the reason is that people are just interested in this technology. You can see things being manufactured and growing in front of your eyes, and it is kind of a little bit bewitching in that regard.
Additive manufacturing as a whole is an extremely complicated issue and a very broad subject. So I must congratulate my 4 guests today, Christopher Tuck, James Buchanan, Dr. Phil Reeves, and Chris Ellsworthy, for sharing their time and managing to cover such a broad subject so well in such a limited amount of time. Thank you.